Okay, let's turn this little light on. So we're going to be graphing the sine function. And before we start, it's important to realize something, because we're going to be looking at the unit circle, the angles on the unit circle, and the points on the unit circle, and translating that to the angle being the x coordinate and the number on the outside of the unit circle being the y coordinate. So that's what's going to happen. It really helps to realize that in advance. So things that we know about sine. We know it is the y coordinate of all of the points on the unit circle. And that since every single point on the unit circle has a y coordinate, the domain of sine equals y is all reals, so that theta can be any real number. The largest that sine can be is 1, and the smallest that sine can be is -1. So the range of sine is -1 to 1 inclusive. We know that sine is periodic because sine is based on the unit circle, and the unit circle repeats. The period of pi, the period of sine is going to be 2 pi, because that's what it takes for us to go around the unit circle. See if I can make this bigger. Oh well. The reason why I have the partial unit circle here on the right is that this is angles measured in the negative direction. So I'm going to start out making a coordinate axes. X is going to be the angle, and y is going to be the value of the sine. Okay. So when the angle is 0, the sine is 0. So sine starts at 0, 0. Let's just look at nice values, and you'll see what I mean by nice. And then we'll connect the dots. So the next nice value of sine happens at pi over 6. So sine is 1/2. So at pi over 6, the sine is 1/2. And then we go to pi over 3. Pi over 2, sine is also nice, because we know that the y value up at the top here is 1. So I've got 0, 0, pi over 6, 1/2. I'm going to go ahead and fill in pi over 3, square root of 3 over 2, and pi over 2, 1. So those are the first 4 points that we're going to look at for sine. Let's go ahead and look at square root of 3 over 2. Especially if I can find my calculator. Oh, there it is. Come on. There you go. Good baby. So square root of 3 is approximately 1.7 divided by 2. We're going to call this 0.9, but it's 0.866. So this is approximately 0.9. And the reason why that's helpful to us is that we're only moving a third of the way. So a third of the way over, we are up to 1/2 from 0. A third of the way more, and we're almost to 1. A third of the way more, we're at 1. And then sine is, it repeats from first quadrant to second quadrant. Well, that means that 2 pi over 3, 3 pi over 4, and 5 pi over 6 are going to have the same values as pi over 6, pi over 3, and pi over 2. So let's see, we've got 2 pi over 3, 3 pi over 4. Oh, we're not doing 3 pi over 4. 5 pi over 6 is going to be 1/2. And then pi, we're back to 0. We know that what happens in the first and second quadrants matches what happens in the third and fourth quadrants, except in the third and fourth quadrant, sine is negative. So let's just see what that looks like. So for this table of values, I let square root of 2 over 2 be approximated as 0.7 and square root of 3 over 2 approximated to be 0.9. But we can get this shape without looking at the 45-degree angles. The thing I was trying to point out was that we know that 7 pi, the sine of 7 pi over 6 is negative 1/2. The sine of 11 pi over 6 is also negative 1/2, so those match up. The sine of 4 pi over 3 and 5 pi over 3, those are both 0.9. And the sine of 3 pi over 2 is negative 1. So that gives us one cycle or one period because we went from 0 all the way to 2 pi of the graph of the sine. If we look at what would happen if we just graphed y equals sine x, you can see that it doesn't start at 0, 0. It starts at negative infinity, which means it never stops, never starts, and it goes equally to positive infinity. And it always has the shape going up to 1, down to 0, down to negative 1, up to 0, up to 1. So it always does that forever and ever. For cosine, we're going to do the same thing, but we're looking at the x values around the unit circle. So we have And let's just see. At 0, cosine is 1. So we start at 0, 1. At pi over 6, we're at 0.9. At pi over 3, we're at 1/2. At pi over 2, we're at 0. And then cosine is negative in the second and third quadrants and positive in the fourth. So here's quadrant 1, quadrant 2, quadrant 3, quadrant 4. A list of the coordinates for cosine is given on the bottom of page 3. And I don't know why I use big red dots, but it makes it pretty easy to trace what the cosine looks like. And you can see 1/3 of the way away from 1, we're at only 0.9 on sine and cosine. So it stays high and then knocks off very quickly. And then it gets almost all the way down, then almost all the way down again, and then it increases very quickly. Let's analyze sine and cosine, the graphs of sine and cosine. So here we go. So we know that sine hits the x-axis at every multiple of pi. At 0 pi, 1 pi, 2 pi, 100 pi, we know that sine will hit the x-axis at every single multiple of pi. And that means that we'll have a horizontal intercept or an x-intercept for the sine at -2 pi, -pi, 0, 1 pi, 2 pi, all the way up. And we could say in general, sine of theta equals f of theta has an intercept at every n pi where n is an integer. And let's just remember that integers are 0, the positive counting numbers, the negative counting numbers, and neither of those ends. So it's every counting number plus its negative counterpoint plus its counterpart plus 0. Those are the integers, and every one of those times pi, the sign of that thing will be 0. It'll cross the x-axis. The maximums, well, let's see. The first maximum that we see is at pi over 2. Let's just look here. The next maximum will be at, here's 1 pi over 2, 3 pi over 2, 5 pi over 2. That's the next max. And then, so to get from the first max to the second, we added 4 pi over 2. We added 2 pi. So we could say pi over
Just,
2. Yes.
uh, just to let you know, you have 10 minutes.
Oh, thank you so much. I really appreciate you. So if we start at pi over 2, we can add or subtract 2 pi, and we'll always be at a maximum for sine. But that's not an easy way to describe every max. So we're going to do this by, remember how we described all of the odd numbers, that the odd numbers were in 2 groups. We had 4n plus 1 and 4n minus 1. And an odd number was either in one or the other. The 4n plus 1s are going to be 1, 5, 5 plus 4, 9, 9 plus 4, 13, etc. And if we go backward, -3, -7. So let's take one of those and just check. Let's try -3. Is -3 in the form of 4n plus 1? So let's see, 4n plus 1 equals -3. How do I know? Oh, if I solve for n, how do I know that -3 is in this format? Yeah, if n comes out to be an integer, then yes, -3 is a 4n plus 1 odd number. If n ends up being not an integer, then -3 was a 4n minus 1 odd number. Well, let's just see. Let's subtract 1 from both sides. We get 4n is equal to -4 divided by 4. Yay! So when n is -1, 4n plus 1 is -3. And that makes it a little easier to see that every single maximum for the sine occurs when we have an odd number of the form 4n plus 1 times pi over 2. So when this number 4n plus 1 is an integer, then 4n plus 1 times pi over 2 is going to be a maximum for the sine, and 4n minus 1 times pi over 2 will be a minimum. For cosine, well, here, let's see, we have a max at 0 pi, we have a min at 1 pi, we have a max at 2 pi. What are we going to have at 5 pi? A max or a min for the cosine?
Min.
That's right, because it's an odd number times pi. So for cosine, if we have an odd number times pi, then we will have a min. If we have an even number times pi, we'll have a max. And every single other number, so 2n plus 1 divided by, times pi over 2. So any odd number times pi over 2 is going to give us an intercept for cosine. Let's pick it up here next time. Wait, this is Monday. Oh, good. We do have another session before break. Good.
All right.
Any questions before we leave?
Um, just like after you end the recording, I'll just like to ask some questions on the supplement later.